Hey there! Welcome to the part 1 of the second chapter of the Deep Reinforcement Learning course, where we're going to dive deeper into value-based method, learn about Q-learning, and implement our first reinforcement learning agent, which will be an autonomous taxi that will need to learn to navigate in a city to transport its passenger from point A to point B. My name is Thomas Simonini, and I'm a deep reinforcement learning engineer focused on implementing AI in video game, and you're watching Deep Reinforcement Learning course version 2.0, a free course from beginner to expert, where you master the skills and architecture you need with TensorFlow and PyTorch. In fact, during this course, you'll build a strong professional portfolio by implementing awesome agents that learn to play Space Invaders, Minecraft, StarCraft, Sonic the Hedgehog, and so more. You can check the syllabus of the course using the link in the description below. And if you're new here, don't forget to subscribe and ring the bell so that you don't miss the next video. So this chapter will be divided into two parts. In the first part, we'll learn about the value-based method and the difference between Monte Carlo and temporal difference learning. And in the second part, we'll study our first reinforcement learning algorithm, Q-learning, and implement our taxi agent. This chapter is fundamental if you want to be able to work on the next chapter on deep Q-learning, which is the first deep reinforcement learning algorithm that was able to play Atari VCS games and beat the human level on some of them, such as Breakout and Space Invaders. But before studying this new chapter, you should master the element that we spoke about in the first chapter, Introduction to Deep Reinforcement Learning. If it's not the case, I put the link of the video in the description below. And by the way, you can follow this video with the article version of the chapter using the link in the description below. So let's get started. So first, let's do a small recap on what is reinforcement learning. If you already know, you can pass this step using the timeline. So, in reinforcement learning, we build an agent that can make smart decisions. For instance, an agent that learns to play a video game, or a trading agent that learns to maximize its benefit by making smart decisions on what stock to buy and when to sell. But in order to make this smart decision, our agent will learn from the environment by interacting with it through trial and error, and receiving rewards that can be positive or negative as unique feedback. And its goal is to maximize its expected cumulative reward. So the agent brain is called the policy. It's the function that will tell us what action to take given the state we are. It's where the decision-making process is made. So it's what we see here. We have our policy that take as input the state and give us as the output an action to take. So the policy defines the agent behavior. And our goal is to find the optimal policy, pi star, aka a policy that will lead to the best expected cumulative reward. And in order to find this optimal policy, and consequently solving the reinforcement learning problem, there are two main types of reinforcement learning method. So the first is the policy-based method, where we train a policy directly to learn which action to take given a state. The second is the value-based methods, where we train a value function to learn which state is more valuable, and then using this value function to take the action that leads to it. And in this chapter, we'll dive deeper into this second set of methods. So we have two types of value-based method. Remember that in value-based method, we learn a value function that maps a state to the expected value of being at that state. So the value of the state is the expected discounted return an agent can get if it starts at that state and then acts according to our policy. But you may ask, what means acting according to our policy? We don't have a policy in a value-based method since we train a value function and not a policy. Well, remember that the goal of a reinforcement learning agent is to have an optimal policy, pi star. To find it, we learn that there are two different methods. The first is policy-based method. Here, we directly train the policy to select what action to take given a state, or a probability distribution over action at that state. In this case, we don't have a value function. So it's what we see here. We give a state as an input to our policy function, and it will output what action to take at that state. So in this case, going to the right. And consequently, we don't define by hand the behavior of policy because it's the training that will define it. On the other hand, in value-based method, we want to find the optimal policy indirectly by training a value function that outputs the value of a state or a state action pair. So given this value function, our policy will take action. But in this case, because we didn't train a policy, since we train a value function, we need to specify its behavior. For instance, if we want a policy that given the value function will take actions that always lead to the biggest value, we'll create what we call a greedy policy. So it's what we see here. We have a state. Our action value function that we train takes the state as an input and outputs the value of each action at that state. So here we see that the value of going right is 1, the value of going left is 0.1, and the value of jumping is 0.2. Then our greedy policy that we define, we didn't train, we just define this greedy policy, selects the action with the biggest state action pair value, and in this case, it selects going to the right. So what we see here is that because we didn't train our policy, we define a policy by hand, so in this case, a greedy policy, and we train a value function, and our policy will use the values of output by the value function to select what action to take. So in this case, the real brain is the value function, not the policy, because the policy is just a function that we define, but the value function is a function that we learn. Consequently, whatever method you use to solve your problem, you will have a policy. But in the case of value-based method, you don't train it. Your policy is just a simple function that you specify. For instance, here, a greedy policy. And this policy uses the values given by the value function that you train to select its action. So the difference is that in policy-based, the optimal policy is found by training the policy directly. In value-based, finding an optimal value function leads to have an optimal policy. It's what we see here. Finding an optimal value function leads to have an optimal policy. So in fact, in value-based methods, most of the time you'll use an epsilon greedy policy that handles the exploration trade-off. And we'll learn about that policy when we'll talk about Q-learning in the second part of this chapter. So now that we understand the real difference between policy-based and value-based, we can study the two different values function. So we already know the first is the state value function. So we write the state value function under a policy like this. For each state, the state value function outputs the expected return if the agent starts at that state and then follows the policy forever after, or if you prefer, for all future time steps. So if we take the example of last time, the state with value -7 is a sum of expected return starting at that state and then taking the action according to our policy. So in our case, we have a greedy policy. Remember that is a greedy policy is a policy that will take action that leads to the state with the highest value. So here, going right, 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 down, down, right. So the second is the action value function. So in the action value function, for each state and action pair, the action value function outputs the expected return if the agent starts at that state and choose this action, and then follow the policy forever after. So if we take again our example, we see that here, instead of having one value for each state, we have 4 state action pair value, because each state we have 4 possible actions, going up, going down, going left, going right. So here we see, for instance, this -7 is the value of being at that state and taking action right at that state. Therefore, we see that the difference is that in state value function, we calculate the value of a state. On the other hand, in action value function, we calculate the value of the state action pair, hence the value of taking that action at that state. However, whatever value function we choose, state value or action value function, the value is the expected return. The problem is that it implies that to calculate each value of a state or a state action pair, we need to sum the rewards the agent can get if he starts at that state. So it means for each one, we need to calculate the cumulative reward an agent can get at that state. for this one, then for this one, then for this one, then for this one, etc. So this can be a dull process, and that's where the Bellman equation comes to help us. So the Bellman equation simplifies our state value or state action value calculation. Because with what we learned from now, we know that if we calculate the value of a state, we need to calculate the return starting at that state, then follow the policy forever after. So in our case, our policy that we define is a greedy policy, and for simplification, we didn't discount the reward. So it means that to calculate the value of that state, we need to make the sum of the expected reward, hence -1 plus -1 and so on, which is equal to -7. Then, to calculate the value of the next state, we need to calculate the return starting at that next state, as t plus 1, which is -1 plus -1 and so on, which is -6. So you see that's a quite dull process, because if you need to do it for each state value or each state action value, it will be very long. Therefore, instead of calculating for each state or state action pair the expected return, we can use the Bellman equation. So the Bellman equation is a recursive equation that works like this. Instead of calculating the value of the state from the beginning and calculating the return, we can consider that the value of any state as the immediate reward plus the discounted value of the next state. So instead of calculating the cumulative sum of reward, here what we can do is that we consider that the value of a state is just the immediate reward plus the value of the next state. To better understand this, if we go back to our example, we said that the value of this state was the expected cumulative return starting at that state, which was -7. If instead we use the Bellman equation, we will say that the value of this state is the immediate reward plus the discounted value of the next state. So in our case, it will be -1 plus -6, which is -7. So we see here that using the Bellman equation, it's easier to calculate the value of each state or state action pair. So to recap, the idea of the Bellman equation is that instead of calculating each value as the sum of the expected return, which is a long process, each value is just equivalent to the sum of the immediate reward plus the discounted value of the next state. And you'll see that this equation will be useful when we learn about Q-learning in the second part of this chapter. So the last thing we need to talk about today is the two ways of learning whatever the reinforcement learning method we use. It's what we call the difference between Monte Carlo and the temporal difference learning approach. So remember that a reinforcement learning agent learns by interacting with its environment. The idea is that using the experience taken, given the reward it gets, it will update its value or its policy. And in fact, Monte Carlo and temporal difference learning are two different strategies on how to train our value function or policy function, depending on the reinforcement learning method you choose. Both of them use the experience to solve the reinforcement learning problem. But the main difference is that on the one hand, Monte Carlo uses an entire episode of experience before learning. On the other hand, temporal difference use only a step, so state, action, reward, next state, to learn. And we'll explain both of them using a state value example. So let's start with Monte Carlo. Monte Carlo, in fact, waits until the end of the episode, then calculates the return, and use it as a target to update its value or its policy. So what it implies that it required a complete entire episode of interaction before updating our value function. So if we take an example, we have this maze. We always start the episode at the same starting point. So we are this mouse, we start always here. We try action using our policy. So in this case, we use what we call an epsilon greedy strategy, which is a policy that alternates between exploration and exploitation. So the idea is that we terminate the episode if the cat eats us or if we move more than 10 steps. And at the end of the episode, we have a list of state, action, rewards, and new state. Then the agent will sum the total reward to see how well he did. Then he will start a new game with his new knowledge, so with this updated value function. And by running more and more episodes, the agent will learn to play better and better. So for instance, if we want to train a state value function using Monte Carlo, we just start. So our value function returns 0 value for each state. Our learning rate is 0.1 and our discount rate is 1, so it means there is no discount. The idea is that during this first episode, our mouse will explore the environment and takes random action that we see here. And the mouse made more than 10 steps, so the episode ends. So here we see that we have a list of state, action, reward, and next state. So we need to calculate the return to see how well the agent did during this episode. So here the return is a sum of all reward. So here it's 1 because we get a cheese. Here is 0, 0, 0, and so on. So it will be what we see here. So the return is equal to 3. So now we can update our value at state 0 using this formula. So the new value of state 0 is equal to the former estimation of the value of state 0 plus the learning rate by the return minus the former estimation of value at state 0. This implies, because we said that the value function just starts to train, so the estimation for each state is equal to 0. So here it will be 0 plus the learning rate 0.1 by the return minus the former estimation, so by 3 minus 0, which implies that the new value of the state 0 is equal to 0.3. So then we start a new game with this new knowledge, so this updated state value function, and by running more and more episodes, the agents will learn to play better and better. So what we see here is that with Monte Carlo approach, we train our agents at the end of an episode. The temporal difference learning, on the other hand, waits only one interaction, so one step, to form what we call a TD target and update our value function. So the idea with TD learning is that we update the value at each step, not at the end of the episode. But because we didn't play during an entire episode, we don't have GT, the expected return that we have when we use Monte Carlo approach. So instead, we need to estimate this expected return by adding the immediate reward RT plus 1 and the discounted value of the next state. So we form what we call the TD target, which is an estimation of the expected return. We speak about Bootstrap because TD bases its update on an estimate and not on a full sample of GT. Why? Because as we said, we don't wait until the end of the episode. We do only one step, so we need to estimate GT. And this method is called TD0 or one-step TD because we update the value function after any individual step. So the idea with TD is that at the end of one step, so state, action, reward, and next state, we have the immediate reward and the next state. We update the value of our state by estimating the return. So how we estimate the return? We're adding the immediate reward plus the discounted value of the next state, and it's what we call the TD target. So then we update our value function for that state, and we continue to interact with this environment with our updated value function. And the idea is that by running more and more steps, the agent will learn to play better and better. So the big difference is that with TD approach, you learn at each step, compared to Monte Carlo, where you only learn at the end of an episode. So if we want to update the value of state 0, let's say that we just start to train our value function. So again, it returns a value of 0 for each state. The learning rate is 0.1 and our discount rate is 1, so non-discount. Our mouse explores the environment and takes a random action. So we see here that it's going to the left. It gets the +1 reward because it got a cheese. And now what we want to do is to update the value of state 0, so the value of this state, using the TD formula. So the idea is that the new value of the state will be equal to the former value of the state, which is 0 because we just start to train our value function, plus the learning rate by the immediate reward, which is +1, plus gamma, so we don't discount, so gamma will be equal to 1, by the value of the next state. But the value of the next state is equal to 0 because we just start to train our value function, so 0, minus the former estimation of the value of our state, which is 0. So the new value of our state is equal to 0.1, and we just updated our value function for state 0, and now we can continue to interact with this environment with our updated value function. So if we summarize, we have whatever reinforcement learning method you choose, policy-based or value-based, two learning approaches. The first is with Monte Carlo. We update the value function, if we take the example of value function, from a complete episode, and so we use the actual accurate discounted return of this episode to update our value function. On the other hand, with TD learning, we update the value function from a step, so state, action, reward, and next state. So we don't play during one entire episode, we play only one step and we update our value function. So what it means we don't have the expected cumulative return, the accurate expected cumulative return that we have in Monte Carlo. So we need to replace it by an estimated return called TD target, which is the immediate reward plus the discounted value of the next state. So that's all for today. Hope you liked the video. Congrats on finishing it. There was a lot of information, so that's normal if you still feel confused with all of these elements. This was the same for me and for all people who study reinforcement learning. So take time to grasp the material before continuing. To help you to grasp it, you can read the article version of this video. The link is in the description below. And if you enjoy the video, don't forget to like it, to subscribe, and to ring the bell so that you don't miss the next video. If you have some feedbacks and questions, please write them in the comment section below. In the second part of the video, we'll study Q-learning and implement our first reinforcement learning agent, a taxi that we need to navigate in a city to transport its passenger from point A to point B. This will be fun. Again, thank you so much for watching, and I'll see you next time and in the comment section. Keep learning. Stay awesome.